fact that there's two different types of anhydrides we can have. The first type of anhydride is one like this, where we have the same groups on both sides of that central oxygen. Remember that an anhydride functional group is your carbonyl, oxygen, carbonyl connectivity pattern. This is a symmetrical anhydride. And this right here is what we call a mixed anhydride, where those alkyl groups on either side of that oxygen are not the same. So this is a symmetrical, and this is a mixed anhydride. When it comes to naming an anhydride, the parent names that we're going to be using will be based on the compounds as if we named them as though they were carboxylic acids. So when we look first at this symmetrical anhydride, we know that this piece and this piece here are equivalent to one another. So if these two carbon compounds were to be named as carboxylic acids, the name would be ethanoic acid. When it comes to naming an anhydride, what we're going to do is first we're going to drop the word acid from that parent carboxylic acid. Then we're going to add anhydride. So up here in this compound, if the parent for our 2-carbon carboxylic acid was ethanoic acid, we're going to drop the acid and add anhydride. So that the name of this symmetrical anhydride right here is going to be ethanoic anhydride. When it comes to this compound here, now we have two different carboxylic acid parents. This one here, if it were a carboxylic acid, this would be ethanoic acid. And if this one were a carboxylic acid, we have 3 carbons, so this would be propanoic acid. So just like we did before, we're going to drop the acid on each of those carboxylic acid parent names. And then when it comes to the mixed anhydride, we're going to alphabetize these parent names and follow them with the word anhydride. So in this case, it's going to be ethanoic, propanoic, anhydride. If we look at another example, like this one here. On the left side of this compound, we have 1, 2, 3 carbons in our carboxylic acid parent. So this would be a propanoic acid. On the right side, we have 1, 2, 3, 4 carbons. So this would be a butanoic acid. And just like we set up above, we're going to drop the acid from each of those parents, and we're going to alphabetize what's left. And so the name of this compound is butanoic, propanoic, anhydride. The next reaction we need to talk about is the synthesis of anhydrides. And so in order to make an anhydride, we're going to be using a dehydrating agent that has the chemical formula of P2O5. So in this case, we're going to take 2 equivalents of a carboxylic acid. So this one right here, this is benzoic acid. If I take 2 equivalents of benzoic acid and I treat it with P2O5, the product that I'm going to get out of that reaction is my symmetrical anhydride. Okay, now P2O5 is a common dehydrating agent. So what we're also going to get out of this reaction is a molecule of water. So if we think about putting these two components together, here are our 2 equivalents of benzoic acid. And so what we're going to do is we're going to remove the OH from one and the H from the other and link the remaining pieces together. Now, that's the synthesis of a symmetrical anhydride. If we were to think about how we might put together a mixed anhydride, it's going to look a little bit differently. So now if we think about a similar reaction in an effort to make a mixed anhydride, let's say we combine ethanoic acid with benzoic acid. We can treat these components with P2O5 and analyze the possible reactions that we can get. Now in this reaction we can get 2 molecules of our ethanoic acid to combine, and that would give us ethanoic anhydride as a product. In the same reaction we could also have 2 molecules of benzoic acid combine, and that would give us our benzoic anhydride. And we could also end up with a product where we had the mixed anhydride, so the benzoic ethanoic anhydride. So all 3 of those products would be possible out of that reaction. So overall, this really isn't the best way to make a mixed anhydride. The better synthesis for that process would be to take an acid chloride, treat it with your carboxylic acid in the presence of a small amount of base, like potassium carbonate, and in that case, you would make that mixed anhydride, like so. The final reaction that I want you to think about is what would happen if we took an anhydride like this one, and we treated this anhydride with sodium chloride. What would happen? In this case, we have a carbon that can act as an electrophile. We have a chloride ion that can act as a nucleophile. So there's really nothing that prevents that chloride ion from attacking either of those carbonyls. What I want you to do is pause the video and think about this mechanism. So hopefully you had an opportunity to think about this mechanism, and hopefully you realize the problem with this mechanism. Because the first thing to recognize is that this carbon is an electrophile, this carbon is an electrophile, and this chloride ion is a nucleophile. So there's really nothing that prevents this chloride ion from attacking this carbonyl. If that happens, we get a tetrahedral intermediate. Now, from this tetrahedral intermediate, we know that it's going to collapse, and we know that it's going to kick out the best leaving group. The 2 possible leaving groups that we have are this carboxylate ion and this chloride ion. This methyl group will never act as a leaving group, so these are the 2 leaving groups that we have to choose from. And there's nothing we can do to change the best leaving group from this tetrahedral intermediate. This chloride ion is the best leaving group. That means that anytime this tetrahedral intermediate collapses, that chloride ion is going to be the group that gets kicked out. And so what we end up with at the end of that process is exactly where we started. So overall, there's no productive reaction in the reaction of a chloride or another halide with an anhydride. We cannot take an anhydride and make an acid chloride from it.